All right, we are going to talk about, we've already talked about triangles, then we talked about quadrilaterals. Now we're going to get even a little bit more general and talk about things that have more than four sides. And these are just lumped into one big category called polygons. So first and foremost, why don't we do and I should say, let me back up a little bit. This video is going to get probably a little bit long. Go ahead and pause it whenever you want to. Also, if you didn't have the chance to print off this PDF document and you're trying to annotate here on your computer, of course you can open up in Notability on your iPad and you can draw all over it, probably the best option. Otherwise, if you're trying to do it on a laptop or a desktop, if you go over here to this comment area, you can see right up top there's a lot of different options for you to add in comments or highlight or add text, different things that you can do there in order to annotate this thing digitally. Okay, so let's go here and let's come up with a formal definition. So whether you're writing right on top or you're typing it in, what is a polygon? First of all, it is a two-dimensional shape that is closed, has straight sides, and does not cross itself. Oops, there we go. I'm really good at writing. That's why I chose to be a math teacher, actually. There we go. Does not cross itself. So if we look at all these examples below, some of them would be considered polygons and some of them just more interesting shapes. So what I would like you to do is go ahead and pause the video and decide for yourself which one of these is a polygon and which one is not. When you restart it, you can watch my solutions. Okay, so let's assume that you have gone through and taken a look at these and now you are going to say which ones are polygons. This first one that looks like a lightning bolt, it does have straight sides, it is closed, it's not crossing itself. I would say yes, that is a polygon. The second one that looks like a heart, it has curved sides, so I'm going to say no, not a polygon. The third one that looks like a moon, also curved sides, nope, not a polygon. The next one, a little bit crazy looking, but it is closed, it does have straight sides, and it does not cross itself, so I'll say yes, go ahead, that is a polygon. The next one, maybe a little bit of discussion around this one. I would say that this all by itself is a polygon, and this is all by itself as a polygon. But if I talk about the shape as a whole, it's crossing itself right here. So I would say no, not a polygon because it crosses itself there. The last one here, yep, that's a polygon. And one more here, not a polygon because it's not closed. If this was some sort of fencing trying to keep animals in, they would all leave. All right, so I'm going to go ahead and get rid of this and do some scrolling. You can do the same. And we're going to go down here and get some more polygon vocabulary. This part here, if we talk about one side of a polygon, it's simply called a side. Right here, we're talking about the corners of a polygon, and there's many of them. We will refer to this as a vertex. Any line segment that connects two vertices but is not a side, you can see the blue segment that I just drew connects this vertex here and this vertex over here, although it is not a side of the polygon. We refer to those as diagonals. Excuse me. And that would be sort of the basic nuts and bolts. If you look at the two polygons that are side by side here, this one we refer to as being a concave polygon, and this one as a convex polygon. You may have seen these words before in your science class dealing with lenses or maybe the little bubble of water that sits up on top of a test tube. But the reason this is called concave is you might think of it as caved in. If you think about, here's a cave, and here we have some little guys walking through the cave or whatever. There is the potential that the ceiling caves in, and now our cave looks more like this. Oops, it's gone in and then gone back out. And so you could think about this also being caved in. A more formal definition is that you can have a diagonal. Again, the diagonal connects two vertices, but is not a side of it. But you can have a diagonal outside. So here's a diagonal that is actually outside of our polygon. Therefore, it is concave. Whereas on the convex one, all the diagonals will remain inside of the polygon. So a little bit of vocabulary there that, again, you'll never be tested on vocabulary for the sake of vocabulary, but as you see it in the context of problems, you'll have to be familiar with it. Okay, again, I'm going to erase this. If you need to see it any longer, go ahead and pause the video, because there it goes. Now we're going to move on here towards the bottom, and we've got a whole bunch of shapes here with different numbers of sides. They are, in fact, all polygons because they are closed, have straight sides, and don't cross themselves. But the number of sides changes. A three-sided polygon, we know that to be a triangle. A four-sided, we talked about that at the end of last semester. That's a quadrilateral. And now, you're probably going to be familiar with some of these. So go ahead and fill them in if you already know them. Some of them you may know, some of them you may not know. Five-sided figure, there is a very large one of these in Washington, D.C. It's called the pentagon. A familiar one also, maybe it looks like honeycomb, a hexagon. A seven-sided figure is called a heptagon. Eight-sided figure is probably, again, very familiar to many of you, octagon. This nine-sided figure is called a nonagon. How many years? 10 years is a decade, so we have a decagon. And then a 12 would be called a dodecagon. Now, these all come from Latin roots. In fact, you might recognize here's September, October, November, December, which at one point in time were the 7th, 8th, 9th, and 10th months of the year. But then Julius Caesar and Augustus Caesar came along and said, we need our own months. So they got bumped to being the 9th, 10th, 11th, and 12th months of the year. It all comes from Latin roots, and as we get into, let's say, a polygon that has 37 sides on it, well, there is Latin for 37, and then put a gon on the end, and that's what it really is called. But what we do instead is we say, if it's got more than 12, and it's not really a familiar name to us because none of us really speak Latin, we're just going to call this an n-gon. So for the purposes of the thing that I just said, we might say that's a 37-gon. It's a polygon that has 37 sides. So these vocabulary words down here correspond to the polygons that you see just above them. One thing to point out about these polygons up here is all of these polygons up here we would consider to be regular. All right, now that doesn't mean they have a lot of bran in their diet. What it means is that they have all sides are congruent and all angles are congruent. We know the first one to be an equilateral triangle. If all four sides of a quadrilateral are the same and all their angles are the same, that's known as a square. This we would just simply call a regular polygon. Again, all five angles inside will be the same. All five sides will have the same length, etc. All of these angles are the same, and as we get into this regular octagon, something that looks like a stop sign, all the sides have the same length, even though it doesn't look like it, but that's a formatting issue, and all the angles are the same. So those would all be considered regular polygons. Again, I'm going to make the ink go away. If you need to see this for any longer, pause the video. All right, now we're going to the back side here, and what we have are a couple of explorations that I will sort of start for you, and then I'll ask you to do some of the work on your own when you pause the video. If you look at the instructions there, it says n is the number of sides, and use a ruler to draw as many diagonals as you can from the indicated vertex only. In other words, please don't, on this pentagon, draw in every single possible diagonal so that you make a really cute star. That's not the point of this one. What we're going to do is we're only going to be drawing diagonals from the indicated vertex, the one with the big dot. And then what we're going to do is we're going to be filling in this table with the information that we have up above. So that means that how many diagonals can I draw in the triangle? Well, if I draw from one vertex to the next, I'm going to actually just get sides of the triangle. I'm not going to get any diagonals. So how many triangles do I have here? Well, there's only one triangle in that first one, n equals 3. And I know that inside any triangle, they're exactly 180 degrees. Looking on to the next one, if I start at this dot, I can draw in that diagonal. But any other diagonals I attempt to draw will actually just be sides. And so when there's 4 sides, there's 2 triangles, and there are 360 degrees. That may be familiar from our quadrilateral unit. Well, now let's go to top polygons that have even more sides. All right, so let's go over here, and again, I'm not going to draw a star inside the polygon, only the emanating from that single vertex. I've created 3 triangles, and if I have 3 triangles, 180 degrees each, that means that I have a total of 540 degrees between those 3 triangles. So you can follow along with me, you can work ahead, but let's fill in the remainder of this table for the polygons that we see there. I'll just be quiet, you can hum a tune in your head or put on Lady Gaga or whatever you want to do. I don't know what the most apt pop song would be for drawing diagonals on polygons, but we'll end up doing that. Go ahead and put in every single diagonal that I can that start from that one vertex. And here it is over here. They end up looking something like seashells by the time we put all these things in here. And now we can go ahead and say, all right, let's put the data on here. So my 6, when n is 6, or the number of sides is 6, I have 4 triangles. And if I do 180 degrees times 4, I end up with 720 degrees. Moving on, when n is 7, that means I have 5 triangles, or a total of 900. Moving on to when n equals 8, that means I have 6 triangles, or a total of 1,080 degrees. When n is, we don't have an example of 9, we do have an example when n is 10, that means I have 8 triangles in there, and so I have 1,440 degrees in there. And then the last one we have is when I have 12 sides, when n is 12. Here we go, n is 12, that means I have 12 sides. 10 triangles in there. That one, the multiplication I can do in my head, 1,800 degrees. Now, of course, looking at the table, we can probably recognize some patterns. If it has 9 sides, even though we don't have a picture, there's going to be 7 triangles in there. And if we have 11 sides, then we're going to have 9 triangles. And if each one is worth 180 degrees, then this will be, let's see, 1,260 degrees. And this will be 1,620 degrees. Okay, what I want you to do now is to pause and figure out, what if I had a 37 gone? What if this number was 37? What if that number was 158? What if that number was n? What would go in the boxes right here? How many triangles would be on inside of it? And how many total degrees would there be in there? Go ahead and pause the video, try to come up with your own pattern, and then you can start the video again and watch my solution. Okay, so you've restarted the video, and let's recognize a pattern. What do we notice is the pattern between the top row of numbers, the one that starts at 3 and goes to 12, and the row right underneath it? Hopefully you guys are going, duh, it's just 2 smaller. So if I had a 37 here, well, there would be a 35 down here. If there was a 158, then there would be a 156 there. If there was an n, then this would be n take away 2. That's how many triangles are inside of a polygon. If n is the number of sides, I take away 2 from that number, and I'll get how many triangles I can draw in there. Now the question is, where did we get that bottom row of numbers, all those degrees that are getting larger and larger and larger? What did we do with 1 in order to get 180, 2 to get 360, 3 to get 540? What did we do? Well, it turns out that we simply multiplied. If I do 3 times 180 degrees, I'm going to get 540. If I do 6, the number of triangles, times 180 degrees, I'm going to get 1080. If I go all the way to here to 10, this was the one I was doing in my head real easy. If I do 10 times 180, I'll end up with 1800. So really what I got to do if I want to get total degrees, I have to take this number, multiply by 180 degrees, and I'll get what's there. So I realize that I may have just confused you a little bit. Let me just back things up a little bit. And I'm going to say, yes, the number of triangles is n minus 2. So if that stands for the number of triangles, I'll do 180 degrees times the number of triangles to get the total degrees that are inside my polygon. All right, so these are going to be these two formulae, or formulae, or formulas, not really sure. Those are sort of what we're going to be applying in many situations in the assignment. Again, this is the, right here, that's the number of triangles, and here we have total degrees. Is right there for any side. So if I said, hey, I've got a polygon that's 143 sides, well, you could tell me how many degrees are inside that thing. All right, again, if you need this, go ahead and rewind it or pause it or whatever. I'm going to get rid of the ink that you can see. And we're going to do this last little bit down here at the bottom. This time we're talking about the angles that are outside of a polygon, not those that are inside, but the ones that are outside. For instance, this one right here. That angle is definitely outside of our polygon. Now, by virtue of the fact that this is a straight line, the two together make 180 degrees, which means this one has to be 65 degrees. If we look here, we already know that this is 90, which means that one's got to be 90. The two of them, again, making 180 degrees. 180 degrees, if that one's 125, that means that this one here will have to be 55. And so on around. I'm going to go around and fill these in. You can go ahead and work ahead of me if you want. But what I'm going to do is I'm going to find all these exterior angles as I go around this shape. The reason why, because all these straight lines add up to 180 degrees. So that's that first shape. That one's got 6 sides. That's a hexagon. Moving on to the pentagon here that's in the middle. And again, I'll just find these exterior angles. Go ahead and work ahead of me. And the last one over here, 67. I'll go ahead and do it one more time over here with my 1, 2, 3, 4, 5, 6 heptagon. And I find that this angle here is 13 degrees, 27, 84, 64, 68, 80, and 24. Okay. Now what I'm interested in you guys doing, again I would like you to pause the video, is go ahead and find the sum or add together all these blue numbers. What do you get when you do 30 plus 65 plus 90 plus 55 plus 45 plus 75? What is, as you go around here, the sum? And do the same thing here. What's the sum here? And again over here, what's the sum of this thing? Okay, as you add together all those numbers. Go ahead and pause the video, get out a calculator, and figure it out. All right, what you probably figured out pretty quickly is when I add these things together, I'm going to get 360 degrees every single time. It doesn't matter how many sides this thing has. It doesn't matter how big each exterior angle is. They're always, always, always going to make 360. Is that weird? It might be. But think about this. If you start, let's go over here, and we start at, in the blue one, and I'm facing this direction. Think about the hand on a clock. So this hand on this clock is starting here, and it's pointing toward, down and a little bit towards the left there. And if I move this thing over here, now my arrow's pointing this way. It has spun a little bit. It's this, maybe it's at, I don't know, 6:30. And as I go over here, now it's more like 8:30. And as I go here, now it looks like it's more towards 10 o'clock. Here, a little past midnight. Here, we're looking at 1:30 or 2. Here, we've spun around and we've gone towards closer to 4 o'clock. And then as we rotate a little bit more, guess what? We're right back where we started. So we've gone all the way around the circle in terms of the hands of a clock. We've gone 360 degrees. So that's the notes that you're going to need in order to get after the problems in your homework. Give them your best shot. We will see each other next week anyways to go back over this. But hopefully that's good background to help you do these problems. They're coming out of your textbook. You can find the textbook on My Haiku. Look for chapter 5, I believe it is. I think it's chapter 5. You'll find page 386. Good luck.